I'm going to immediately give it over to our first speaker. Shelley we don't really have leads on the Electron team, but if we did, she would be one of them. Shelley has been working on Electron for a few years now. She works on Electron full-time, handles a lot of the core components. And this morning, she's going to talk to you about everyone's favorite topic, garbage collection. Super important for performance and the memory your application uses. Quick show of hands, how many people have at least thought about how much memory the Electron app uses? Yeah. If you have less trash in memory, you're using less memory. So please give it up for Shelley.
Hey, everybody, and thanks for that great intro, Felix. Like he said, I've been working on the Electron project full-time now for about 2.5 years. This work has also allowed me to explore and actively contribute to a pretty wide range of open source projects and committees besides Electron, like TC39, Chromium, V8, and Node. I'm based here, and I'm excited to talk to you today about taking out the trash. So today, I'm going to take some time to talk about that. What's garbage collection in the context of Electron? We're going to talk about what it is, how it works in Electron and JavaScript at large, and then go over a little bit of some of the key information that you should be aware of in order to better manage memory within your Electron apps. So, what is it? At the highest level, garbage collection is a form of automatic memory management. Garbage collection allows you to reclaim garbage, which is what we call memory, that's occupied by objects that are no longer in use by the program currently being run. As a higher-level language, JavaScript automatically allocates memory when objects are created, and then frees them when they're not being used anymore. This automatic nature, while helpful in reducing the cognitive overhead as your users write code, this can also be a potential source of confusion. It can give developers the false impression that they don't need to worry about memory management. And while they don't need to worry about memory management in the same way as they would when writing something like C, it's not really to say that you can keep it out of sight and out of mind. Before we dive into the details of garbage collection in Electron and JavaScript, let's take a bit to refresh ourselves on how memory is used and recycled within a given program. In most every programming language, memory lifecycle maps to a repeatable pattern with 3 distinct stages. First, we're going to allocate the memory that we need. This is explicit in lower-level languages like C, where we'd call something like malloc. Since JavaScript has garbage collection, this is handled for us and is thus implicit. Then, in the second stage, we're going to use the memory that we just allocated. This can't really be done implicitly, as it's what comprises the bulk of a given program. If this part was implicit, we just kind of wouldn't have code. And then finally, once we've used the memory that we've allocated to fulfill its purpose, we then deallocate it. This is, again, explicit in lower-level languages like C, where we'd call something like free, and then implicit in JavaScript. This first stage, memory allocation, can take one of a few forms. We can allocate memory by initiating a value, or we can allocate memory via function call. Some examples are here. On the left-hand side, we're going to allocate memory via value initialization for a number, a string, and then an object with some values contained therein. On the right side, you can see some examples of memory allocation by means of function call. However, since it's not always perfectly clear-cut, at the bottom there, you can see a call to string.substring. Since strings are immutable values, JavaScript may actually decide not to allocate memory and just store the 0 through 9 range instead. This next step is the step that's done by the user regardless of language. Using allocated memory takes the form of reading or writing in allocated memory. For example, here we allocate some memory for a string, which we set to CovalenceConf. We then use this allocated memory by passing it to a function, which logs that string to console. Finally, as the last step of the memory lifecycle, we need to release the memory that we've allocated once we no longer need to use it for anything within the context of our program. This is where it gets a little bit tricky, so hold on to your hats for a second as I dive into a few core computer science concepts. Freeing the memory itself is pretty doable, but that's not what makes this stage tricky. The question we actually need to be asking ourselves here is, how do we know when we need to free a given piece of memory? What makes something garbage collectible? This question brings us to a key concept in computer science and logic, that of decidability. In logic, a true-false problem is undecidable if it's been proven that there's no effective method for determining membership that can exist for that problem. In other words, in order for a problem to be decidable, there needs to be an algorithmic solution that, given any arbitrary input, will correctly produce yes or no for that input. In terms of garbage collection, what this means for us is that there's no way to algorithmically determine or to write an algorithm that will tell us with 100% accuracy whether or not something needs to be garbage collectible. Okay, so that seems kind of grim. Does that mean we just accept that we're going to be bad at this forever and ever? Not quite. So what we can do instead, actually, is reduce this undecidable problem in scope to something that is decidable. So there's two main such reductions that exist for garbage collection. These are reference counting and mark and sweep. In reference counting, what we're going to do is reduce the question of garbage collectability to whether or not that object has any other objects referencing it. If an object has nothing referencing it, then we say that it's garbage collectible, and we free it. Our main issue with this approach is circular references. If two values reference each other, then, like the Spider-Man meme, they're just going to point to one another forever and ever, and nothing's ever going to get freed. So the second, and notably more effective, reduction for garbage collection is known as mark and sweep. As of 2012, actually, all major browsers ship a mark and sweep garbage collector. What we're going to do here is we're going to reduce the question of garbage collectability to whether or not an object is reachable within the runtime. As such, any object currently reachable will be kept, and then any unreachable objects will be garbage collected. This process has two stages. The first is marking. Marking is the process by which reachable objects are found. The garbage collector will start at a set of known object pointers, which they call the root set. This includes the execution stack and the global object. What we're going to do then is we're going to follow each pointer to a JavaScript object and mark that object as reachable. We're going to continue doing that recursively until every object reachable in the runtime, starting from the root set, has been marked as reachable. Everything else that's left will be unreachable. As the name suggests, the sweep phase of mark and sweep sweeps the objects away. That is, we're going to clear the heap memory for all of the unreachable objects. All those objects that were marked unreachable in the mark phase we just went over are going to get cleared out, and the others will be spared. To prepare for the next round of marking and sweeping, after we've cleared out all the unreachable objects, all of the marked objects are going to be reset as unmarked, so that we can prepare for the next round. In the future, when we need to allocate new memory, we're just going to look at the available heap and then find an appropriately sized chunk of available memory. So I can probably proceed on the assumption, given the reason that we're all here, that we're all familiar with Electron, but I'll do a 30-second rehash just to make sure. Electron, as a JavaScript framework for creating desktop apps with web technologies, can be used on Windows, Mac, and Linux, as well as a variety of other platforms, like Raspberry Pi or Windows on ARM. It works by integrating Chromium and Node. and then adding in an extra slab of C++ and Objective-C code, which it uses to allow it the ability to create fully formed GUIs, as well as access file system and networking capabilities with Node. So fewer of you are likely familiar with V8, so we'll dive into it a little bit now. V8 is Google's open source, high performance JavaScript and WebAssembly engine. It's written in C++, and it implements the ECMAScript specification. What this means for us is that it allows Electron to create JavaScript objects, classes, and everything else that you're familiar with in JavaScript, but in C++. It also contains, importantly, a mark and sweep garbage collector, codenamed Orinoco, which has two components, major and minor. The minor garbage collector relies on something called the generational hypothesis. Computer science research over time has resulted in an observation that most allocated memory falls into two categories within a given program. Firstly, most allocated memory becomes unused quickly. Secondly, the parts of memory that are allocated and don't become unused quickly live for a very long time. This has allowed V8 to segment its heap into two sub-collectors for garbage collection, as I just mentioned, major and minor. So the V8 heap splits itself into what are called generations in order to exploit what the generational hypothesis tells us about object lifetimes. Here, we can see a slightly simplified diagram showing us the layout of the heap. The younger of those two generations is itself split into two parts, for reasons that I'll explain in a second. Objects start out in the younger generation and are moved through successive generations every single time a garbage collection occurs. V8's minor garbage collector, called the scavenger, exclusively collects objects from this younger generation. This generation is likely to need very frequent collection, owing to the fact that most of the objects allocated are moving quickly out of scope. It also cheapens the short-lived objects significantly, as your apps will only need to pay down the cost for objects that survive scavenger collection. If an object survives 2 rounds of garbage collection, V8 moves it to the old generation. The major garbage collector, in contrast to the scavenger, collects garbage from the whole heap. I'll avoid diving too deeply into the weeds here, but this comprises 3 stages: marking, sweeping, and then finally, memory defragmenting. Combining these 2 collectors, in addition to doing work in parallel, concurrent, and incremental ways, has made V8's garbage collection pretty efficient and well-suited to allowing you to write more performant apps. So, how does Electron play into all this? Why am I even telling you about this? At the very beginning of my talk, I said that the automatic nature of JavaScript garbage collection can lead to a little bit of a false sense of comfort and security in regards to how much JavaScript developers need to concern themselves with memory management. And that's arguably more true in the context of Electron than it is in the context of the web. A very noticeable and key example of garbage collection and how it interfaces with Electron can be seen in the UI. UI considerations require different strategies around memory management and garbage collection than one might expect. And failing to write code with these strategies in mind can lead to some pretty unexpected application behavior. For example, instinctively, we might assume that we shouldn't collect any given piece of UI, like a browser window, until that window has been closed or destroyed. However, since we're using V8's garbage collector, we know that they've reduced the question of whether or not memory should be collected to whether or not an object is still reachable in the runtime. As such, if you run the code in the snippet you can see on the screen right there, you'll find that this window will actually just disappear on you within a few minutes. What's happened is that since you've instantiated the variable in a listener callback, the window variable is going to go out of scope. And so the V8 garbage collector has taken this as its cue that piece of memory can be deallocated and swept away. A very useful concept for us as we think about this is that of weak references. A weak reference is a reference to an object that allows you to get that object without affecting whether or not it's going to be garbage collected. It also allows you to be notified when the object has been garbage collected. Right now, however, unfortunately, there's no real way to create weak references within JavaScript, since the language doesn't have a way to directly assign them. The only API in JavaScript related to weak references now is the weak map. But since it only creates keys that are weak references, it's impossible to know when an object itself has been garbage collected. There is, however, a stage 3 proposal for a new weak ref class in JavaScript, which means that some browser engines have already started to do some of the work necessary in order to implement it. Having access to user-defined finalizers would be a significant game changer for JavaScript and Electron, as it would allow for actions to be run after objects have been garbage collected, and thus make it a lot easier to handle contingencies that right now aren't possible without really diving into the deep and kind of wild world of native Node add-ons. There are ways, however, to access some of the garbage control functionality from the context of your Electron application. To accomplish this, we can pass a command line flag to Electron, which takes the form --expose GC. What this is going to do is it's going to add a new GC function to the global object in JavaScript, so that you can then request a garbage collection to occur. This is not, importantly, a panacea for your memory issues. Garbage collection is itself actually pretty intensive, and so it should really only be used with care and intention. So you can pass an options object to this GC function to more specifically tell Orinoco what kind of collection you'd like to perform. By default, without that parameter, by just running GC with parentheses and no options, what you're going to get is a synchronous major garbage collection, meaning that collection will be performed synchronously over the whole heap. This options object allows you to choose between major and minor garbage collection, and synchronous versus asynchronous garbage collection. You can mix and match these options as you wish. So let's take a quick look at this using Electron. Here, we're going to pop up a browser window and then instantiate a single empty object. We're going to use it somehow, pretend that we're going to use it to do something or other, and then we're going to set it to null. It's now been through the whole memory lifecycle and is ready for garbage collection. It died pretty young, so it's almost certain that it'll be in the younger generation of objects. If we invoke a synchronous garbage collection using the scavenger collector, its associated memory will be freed and then prepared for later use. So why do we even want to use this flag? How could you, as consumers, take advantage of this? Taking advantage of this can be helpful in several ways, but two spring to mind most directly. Firstly, you can use this to better understand how much memory you're holding onto at certain points in your app by watching how memory changes in monitoring tools or in combination with app.getAppMetrics, which is a function that Electron exposes on its app module. Secondly, you can use this to monitor application performance and to see how it's affected by freeing up that unused memory. Beyond the one we've just discussed, V8 actually exposes a pretty solid series of other flags that affect garbage collection behavior. You can see a list of them all yourself by running the command I show you on screen here in a terminal of your choice. That would be node --v8 options pipe grep gc. But I'll run through some of the ones you might be interested in quickly here and now. The first of these, --trace gc, makes it so that a new garbage trace line is printed to console after each garbage collection. This output is a little bit dense, but you could definitely leverage this to see how application performance corresponded to each garbage collection at a much more granular level. You can also change the determinant for performing a garbage collection within Electron using the flag --GC interval. V8 doesn't really make it clear what precipitates garbage collection by default, but you can override that to ask the garbage collector to perform collection after a certain number of memory allocations, either by value instantiation or allocation via function call, as I mentioned towards the beginning of my presentation. The previous flag allows you to use the number of allocations as a determinant, but you can also pass a flag to change the rate of garbage collection such that it happens on a more predictable schedule, instead of unpredictably based on V8's internal and somewhat opaque optimization strategies. When you pass --predictable GC schedule per V8 documentation, this can actually help you fix some issues with heap growing and idle and memory reducing behavior. Finally, you can also gain a better understanding of the way that garbage collection is being performed on different objects by passing --trace GC object stats. This dumped data is admittedly a little bit dense as well, but with a little effort, this is potentially a goldmine for detailed information about how each object in your application is progressing through the memory lifecycle. This might, for example, show you that something is hanging around in your application a lot longer than you expect that it is, which might clue you into ways that you can ensure your code's being written in such a way that the garbage collector can free it as soon as you're done with it. So far, we've talked about garbage collection as a concept and gone over some of the ways that its most basic tenets are surfaced within the context of Electron. Finally, we're going to take a look at some of the sneakier ways that your code can cause memory problems in your application, and some of the best ways to prevent and fix those issues. The two key areas that we'll be honing in on are accidental globals and poor scoping. Global variables in JavaScript are those that are attached to the window or declared outside of any given function, and are thus accessible to you anywhere within a program. These variables have their place, and as we'll see, are sometimes necessary, but they can also present some pitfalls for garbage collection within your app. For example, if you reference an undeclared variable within a function, a new variable is actually going to get automatically created on the global object. If we look at the example to the left-hand side of this slide, we'll see a code snippet where the variable something is set to the string "oh no." Since we forgot to preface something with let or const, it was automatically attached to the window object and inserted into the global scope. This same thing happens if we attach something to this. When we call the function this in the window object, we also inserted something into global scope. What this means for us, from a garbage collection perspective, is that something will never be garbage collected while the program is running, which, given that we only referenced it inside one function and nowhere else, probably isn't what you wanted. To prevent this from happening, you can set useStrict at the top of your file. This, amongst other things, prevents the creation of accidental globals. The next common issue is vaguely similar. As I mentioned before, with the disappearing window problem, users will often mentally reduce the question of whether or not something is garbage collectible to whether or not it's visible on the screen. Unfortunately, this is not what V8's own garbage collectors do. So if you create a UI element inside a function and assume that it will be kept alive for the entire time that it's needed on screen, get ready for some Houdini elements. To help you prevent some of these kinds of issues preemptively, you should be actively working to instantiate variables, such that every UI element you plan to show on your screen has an active reference for the entire lifetime of its intended usage. Many JavaScript developers writing code for the web don't really consider garbage collection on an active, everyday basis. And for the most part, that's pretty much okay. You can get by in JavaScript with a cursory knowledge of garbage collection, but you're going to write more robust code when you consider it more actively. Electron asks you to think a little bit more directly about how we take out the trash, with a little added knowledge of how garbage collection works under the hood. As you go back to work next week, I'd like you to take with you these 3 main things. Actively consider your UI element lifetimes. Some things are collected more quickly than you might expect, and you're going to save yourself some significant headaches if you're not playing whack-a-mole with your windows. Secondly, profile your heap usage. You might be surprised at what's hanging around and how easily you can make performance gains by paying a little bit more attention to that. And finally, watch your globals. Unbounded memory leaks are our common enemy, but I know that collectively we can run into 2020 writing better apps and continuing to grow the Electron community to the benefit of us all. Thank you very much.
Every talk, we have a bunch of minutes set aside for Q&A, and this is one of them. And I heavily recommend using this time if you want to know anything about the deeper Electron internals, or anything about the talk. Well,
is there a magical way to turn on use strict just globally for an Electron app?
Not right now, actually, but that's an interesting question. Some of the files in Electron itself do have that, but in general, it's sort of left up to the user whether or not they would like to enable that.
For the for the manual GC call,
yeah.
Can you access that in the render process as well, or is it only in like the Node.js main process?
You should be able to access that in the render process.
Okay.
Anywhere you can access like the global object, it'll be attached.
Hi, I have a question just about like module exports. If I have a bunch of different node files, let's say I assign a bunch of variables and make functions, and then I never export them. Are those sticking around in memory too?
Those would be garbage collected. If there's no active references to any given object,
Cool.
V8 will mark it as unreachable per se, and then like garbage collected. How fast that's done is kind of a different question. It's pretty. I don't really think that like V8. So like the way that V8 memory management works is that like unless you like override the way that it's done to like force predictable scheduling, then it basically just kind of like does it whenever it like determines by like kind of black box means that that's the time. But in general, it's pretty efficient, which is why like I would only really recommend like overriding that and exposing that kind of a flag if you're like specifically trying to figure out where like memory leaks or issues are within your app.
Hey, so for the Ornico method in V8, when it survives, 2 rounds of GC and becomes in the old category,
Yep.
Does that mean that it never gets GC'd, or is it like less likely to get GC'd?
So what that really means is that when something is in the younger like split set of generations, then it's kind of under the like jurisdiction of the scavenger collector. So if it passes those 2 garbage collection rounds and ends up in the older generation, what that means is that it's still totally available for garbage collection, but scavenger runs more frequently, whereas like the older, the major collector runs slightly less frequently. So that just means that it won't get collected until it's marked unreachable, and then the major GC runs.
Hi. I have a question. Like I've seen the issue of the UI disappearing when we click outside the screen a lot. So can you explain more about that? I just saw one slide, but can you talk more about that, how to fix that?
Yeah, so if you, for example, the 2 ways that this comes up a little bit more commonly are with trays and windows. So let's say that I create a tray inside like a single function and then never reference it again or keep a global reference to that variable. Then what's going to happen is that, like, let's say const tray equals new tray, blah, blah, options, path to tray. Once that goes out of scope, then V8 is going to mark that tray unreachable. And V8 doesn't really care about the fact that you're still wanting to show that tray on the screen, which means that like when that gets garbage collected, your tray is just going to like disappear, pretty much. So there's some ways that actually Electron overrides some of that natural behavior. Like, for example, if you have a memory that's openly showing, we like override some of that functionality so that menus can't get garbage collected while they're actively open. But in general, a lot of that behavior is kind of like left up to the user to manage and make sure that like when you create a browser window, you're keeping a reference to it around outside of a given function as long as you actually need that thing to stay alive. So like if you look at like any default fiddle or Electron quick start, you'll see that's why like let win or let mean window is up above the like actual instantiation of that variable inside the listener callback for the ready event on app.
You mentioned when one of the JS flags that you passed in was outputting something to their terminal as far as like what the GC was doing.
Yeah.
Does that function actually return something while you're running it, and can you inspect it actually in there? Or is it just return nothing or undefined or something?
Yeah, it returns nothing. So like what you do is you'd, in Fiddle, for example, you could check this out by inside the preferences section of Fiddle, you can pass runtime flags. So what you'd want to do is just like pass that runtime flag to start up when you like start up your local Electron executable. And then once you have that, if you look in like the console section of, you know, Fiddle while it's running, then you could see like those things getting dumped progressively after every single GC. So like you just kind of call it and then it starts showing up pretty much.
Kai.
Do you have any recommended alternative tools to just outputting the garbage collection to console? Any other alternative profiling tools that you would recommend using if you wanted to get really sophisticated with like visually looking at the object tree?
Honestly, not off the top of my head. V8 like doesn't V8 doesn't really document like a lot of things, but if you run like the --v8 options flag inside Node, there's actually like a lot of options. Like if you run even like running like grep GC doesn't even give you all of them. There's probably close to like 20 or 25 different ways you can look at like how GC is working within V8. And I honestly just recommend like if I was writing my own app, like I'd probably just be playing around with a combination of all those flags. And seeing like which one gave me like the critical mass of information I felt like I could use to best profile what was hanging around or working in ways that I didn't expect or didn't want or that was adversely affecting perf.
Thanks.
Do you recommend any linter plugins for like sensing when something's GC good or not?
Any what plugins?
Like linter plugins, like something that may highlight like, oh, like this is going to get garbage collected. Maybe do something about it. I don't know.
I don't actually know if any of those exist, but that actually would be a really good tool for someone to write.
Yeah, maybe
now
we
that
should
I think about it.
We should maybe build that. It actually sounds pretty good.
Is there any way to pause garbage collection? Like if you want to say not do it for a while because you know you're going to be doing something that you like don't want interrupted? Is that exposed?
So you could do something if you wanted to. Like if I was going to do that, I'd probably just pass like one of the flags that set memory or that set GC based on memory allocation and just set it to like 9999999. That's like what I'd probably do for that. There might be a way to do it in like a bespoke kind of a flag way, but like off the top of my head, based on stuff that I've actually like done in my own apps, I would just set the like flag that determined that to like an absurdly high number so that it wouldn't happen for a really long time.
Yeah, could you speak to any tips you might have around managing GC and how GC gets managed around async await, especially because await is keeping execution state around, and any implications that might have?
Can you be a little more specific, like in terms of like how garbage collection like interfaces with asynchronous functionality?
Yeah. So kind of things to watch for if as we kind of enter this world where we're going to be using async await more. What are the kind of the implications for GC, if any? Okay, so like from an event loop perspective, the way that like asynchronous functionality kind of works, if we use like promises as a specific example, is that promises run, like promise resolutions and rejections like technically run off of the main event loop,
they run in what's called the microtask queue. So like that basically means like we want to run that promise fulfillment or rejection like at some point in the future, but before the next primary event loop tick happens. So typically garbage collection, like the more naive style of garbage collection, is known as like stop the world, which is why I say like you do want to use it a little bit sparingly, because it does actually like stop a lot of like the functionality happening in the rest of your app if it's done naively. V8 has done like a lot of optimization around that. I think I mentioned briefly that it's parallel, it's concurrent, and it's incremental, which means that V8 has sort of optimized their engine to do a lot of work, or as much work as possible, when like your app is idling, basically. So I would say that there's not really any specific considerations you need to make around asynchronous functionality and garbage collection, in the sense that V8 has done like quite a lot of work to make it so that you shouldn't see any adverse effects of like running GC like interspersed or whatever within asynchronous functionality. Does that help?
Yes. Very much. Thank you.
Have there been particular parts of the Slack app that are prone to memory leakage, like in the main versus render process or RxJS or anything like that? Anything you can talk about?
It's a great question. I'm slightly less qualified to answer that one because I don't work on Slack. I would say maybe find a Slack person somewhere here to ask that question. But in general, like the line that I'll always kind of use for those things is that Electron is a toolbox. Like the way that you use like a consumer's performance is not necessarily a reflection of Electron, in the sense that like, there's definitely apps out there that like proverbially hammer in their nails with like a screwdriver. And like we recommend you don't do that, but there's not really a whole lot we can do to like force you to not do that.
Maybe I can answer that a little bit. Yeah. So Slack, like I think most applications, we're not there yet. There's a lot of improvement we can do, and we sort of do that every single day. To explain that maybe a little bit, we have this internal channel where all day long we do nothing but look at memory profiles. So whenever you have a case like that, we actually would be super interested in it, because it seems to sometimes depend on various configurations and edge cases. I'm going to tell this actually to all of you. If you have any kind of issue with Slack, you can write /feedback your issue, and it will like reach an engineer eventually, and we're actually super thankful for that. So whenever you have any kind of issue, we do have a lot of engineers who care a lot about performance. There's probably a lot of work we have left to do, and every single day we try to get a little better. All right, going once, going twice. Thank you all. Those were one more.
Could you talk about string garbage collections? Because I think strings are kind of special in V8.
Talk about what garbage collection?
Strings.
Oh, that's a great one actually. I don't know if I have full context on that, just because I didn't do a lot of research into like how specific different types of like types in JavaScript are garbage collected. More about like the object process for garbage collection as a whole. But returning back to like one of the things I mentioned like towards the very beginning of the presentation is that strings as like immutable objects in memory are stored a little bit differently, in the sense that like when you call substring, for example, like JavaScript might decide, depending on how the engine that you're using is implemented, like SputterMonkey. SputterMonkey, for those who are not familiar, is like the corollary for V8 in Firefox. Basically, each of those engines like implement the ECMAScript specification, but in cases where like the spec is like a little bit unclear, there might be some differences between those engines, which is why if you ever notice like different behavior in Firefox or Chrome, it's because like the engines are different. But basically, like at a like higher level, depending on how the engine that you're using has decided that it wants to allocate memory, and memory may or may not be allocated depending on what you're doing with strings. But otherwise, like beyond that like special case, they are handled fairly regularly, in the sense that as soon as like there's no reference to them, they'll be GC'd. Yeah. Any more like specific? I don't know if I can shed more specific light on that.
Okay, cool. Those were awesome questions. Keep that energy up. That was good. Once again, please give it up for Shelley. Thank you.